Hello everyone, my name is Zhezha Lin. The title of this paper is Accelerate Binarized Neural Networks with Processing in Memory Enabled by RISC-V cosine instructions. And this is a joint work with my advisor, Professor Zhenkun Li, and we are from National Tsinghua University in Taiwan. And this is also a joint effort with Howard Wang and Miri Hong, who are from MediaTek. This is outline of this presentation. First, we will have introduction and technical background, and then we will describe our work with processing in memory architecture and cosine instructions, and then TVN compilation flow, and one example of binarized convolution, and experiment result, and finally we will conclude this work with conclusion and future work. Here is a brief introduction for this work. Nowadays, there are emerging technologies trying to take down the memory wall, and one of the techniques is processing in memory. This work exploits processing in memory to accelerate binarized neural networks, and we have done the following 5 tasks in this work. We take convolution of binarized neural network as target application, and we model processing in memory in Gen 5 for supporting bitwise operations and population count. And processing in memory operations are supported as RISC-V cosine instructions. Binarized neural networks are compiled and deployed by TVN, and we propose a memory layout suitable for processing in memory. Next, we describe the processing in memory principle we use for this work. This kind of processing in memory is to perform bitwise operations on memory rows, and is to use sense amplifier to accomplish the operations. The following is a demonstration of the memory device, and for a regional read operation, a whole row of memory cells will be activated, and the activated cell will be read out to the sense amplifier for later use. And for doing bitwise operation on the memory device, 2 rows of memory cells will be activated at the same time. So 2 memory cells can be read by 1 sense amplifier, and we can set the threshold of sense amplifier to do bitwise operation. Take AND operation for example. We can set the threshold to read out 1 only when 2 cells contain 1, and the other situation will read out 0. And the OR operation can be done with the same manner. In this work, we use TVN for compilation. TVN is an AI compiler framework, and it supports different AI model formats. And there are 2 intermediate presentations in TVN, and we target the relay IR. Relay IR is to present the AI model as a graph composed of operators. And there is a feature in TVN called Bring Your Own Code Gen. And this feature is to extract operators inside the relay IR graph and replace them with the implementation outside TVN. And we use this method to deploy our processing in memory operations. And this is our processing in memory architecture we modeled it in Gen 5. On the left hand side, this is a typical CPU, and we add new memory controller command to activate the processing in memory operations. And in this CPU, it also supports the processing in memory instructions we modeled it. And on the right hand side, this is a memory device, and the sense amplifier can do the bitwise operations for the memory cells. And there is a popcorn engine because the sense amplifier can only do bitwise operations, but we need popcorn operations for binarized convolution. And there are our processing in memory instructions. We model 3 instructions in this work: AND, NOT, and popcorn instructions. And the operands for this instruction are memory address, because we need to represent a whole memory rows. And here we demonstrate the behavior of our instructions. The AND instructions will make 2 memory rows to do AND operation and store in a target row. and the NOT instruction will make a memory row to do NOT and store in the memory row. For popcorn instruction, it also operates on a whole memory row, and we can set the length for each operating unit. If the length is set to a byte, which is 8 bit, then we count the number of 1 in this byte, and the result will be output. In this case, the number of 1 is 3, so the output will store the number 3. And there is an immediate section in our instruction format. This immediate set the length of operating unit. If the length is set to 1, then you operate on 1 byte. If the length is set to 2, then you operate on 2 bytes, which is 16 bits. And now we describe the TBN compilation flow. The BNN models are from TensorFlow, and when it was imported to TBN Relay IR, the binarized convolution will be represented with 2 operators in TBN. One is BPEG operator, and the other is BIP serial convolution 2D operator. And we will use BYOC to replace the bit serial convolution 2D, because this is the actual computation for the convolution. And the new PIM bitconf 2D will use eternal C code to utilize the processing memory instructions. And this C code will need a modified RISC-V toolchain to compile. And finally, the compiling model will run on the Gen 5 simulator with RISC-V cosine instruction support. And now we will show an example of binarized convolution. And we will show a normal version, and then we will show a PIM version. In the example, the input and weight are quantized to either 0 or 1, and the BPEG operator in the TBN will pack the data along the channel axis. And in this case, the channels is 8, so there will be 8 elements of 8-bit integer, like this. And then these 8 elements will be packed to 1 element. And this 1 element will take the bit pattern from the 8 elements. So this bit pattern represents value 100. So the resulting element will store the value 100. All the input and weight will be packed by BPEG operator. And after packing, the multiplication and addition of the convolution will be replaced by AND operation and popcorn operations. And for the input to do the operation, you will need to correspond with the weight matrix. So there will be a sliding window on the input. The first round will do this 9-element input with the weight, and the second round will do the next 9 elements, and the third round will do the third 9 elements, and so on until it goes through all the inputs. And these are the operations for a normal version of binarized convolution. First, input need to do AND operation with weight, and this is like doing a multiplication for normal convolution. And after we get the AND results, you need to do population count to count out the ones. It's like doing the addition of the normal convolution. And after we get the result of population count, we need to sum up these 9 numbers. So there will be a summation at the end, and it completes the convolution operation. For processing memory version of binarized convolution, we first need to turn the layout to be suitable with the row-based operations. And to do that, we first take out the first sliding window of the input and flatten on a memory row. And then we take out the second sliding window of the input and also put it flattened on the memory row. And the third one of the sliding window and put it flattened until we take out all the input sliding window and make it to the format of a memory row. And also the weight should do the same, but the weight data operate with the sliding window are the same data. So we need to duplicate the weight on the memory rows. After change the memory layout of input and weight, the input memory rows and weight memory rows can do AND operation using the processing memory instruction. And after doing AND operation, we can use the population count instruction to get the result. And because our population count operation can operate on a long length of elements, so the summation operation can be replaced. So after the population count, the result will be the same as the normal version of the binarized convolution. This is our experiment setting. The dream file is set as the following table, and the BNN models are from Reptile project, and we take SqueezeNet and VGGNet and NXNet from this project. And these models are trained in TensorFlow and use TVN to inference. And this is our software version. This is our experiment results. The best version uses only CPU to run the model, and the PIN version uses PIN instruction and the memory layout transformation to accelerate the convolution layers. All the model runs on our Gen5 simulator and get the simulated execution time. And we can see that the speedup is from 3 to 57. Because the range of our speedup is very large, so we list the time-consuming layers for these three models. Because the SqueezeNet have the most convolution layers, so it has the best speedup. But for the other two models, the speedup is not that good because its convolution layer is much less. And finally, these are the conclusion and future work. We create a flow using PIN operations to accelerate the BNNs, and PIN operations are modeled in Gen5 simulator. We support TBN compilation for PIN implementation. A memory layout suitable with PIN operations is proposed, and the results give speedup from 3.7 up to 57.3. And for future work, we would like to integrate the PN become in TVN, and so that optimization inside TVN can be applied. And maybe we can support more complex operation with this type of PN, so more types of AI model can be supported, like CNN model. And this is my presentation. Thanks for listening.